Hello and welcome to Calculus 3. Chapter 11, Section 1, Vectors. Let's talk about basics and then go home. So, what is a vector? A vector is a mathematical construct which doesn't exist. That's the first, like your numbers don't exist, right? You don't see number 7 walking down the street. So vectors are mathematical abstractions, just like numbers are. And they are a little bit more advanced than numbers because their magnitude might represent a number, but they also have a direction. So they're instead of being explained by one quantity, like a number, 7, and that's it, it's a quantity, vectors have 2 degrees of measurement. One is the magnitude and the other one is the direction. Now vectors can live in any dimensions that you need them to live in. They could be one-dimensional, in which case they collapse down to just numbers, which is just the magnitude. But then again, you have a positive and negative, so you can say, all right, fine, still 2-dimensional. You have a 2D vector which lives anywhere in the 2D coordinate plane, and then 3D, 4D, and if you take linear algebra, whatever amount of dimensions you want to. Now, vectors can explain anything or portray anything. For instance, I can say that I am currently a vector in space. As I stand upright over here, the magnitude of this vector is 6,1. That's my height, right? We can convert that to meters or centimeters if you want to. But if I am 6 feet and 1 inch tall, then the magnitude of this vector, and then I have a clear orientation which is upright, right? At some point tonight, my orientation will be horizontal, right? In which case I will be a different type of a vector. It's the same magnitude, different direction. So vectors can represent anything. You can talk about coffee cups and elephants and desks and whatever else you want to, but you can also plug the functions and you can plug technically anything else. So a vector is a mathematical construct that has magnitude and direction. If I have 2 points in space, I call them P and Q, I can stretch a straight line between those. I will have the initial and terminal point, also known as tail and head. Also initial and terminal. So initial point and terminal point. And vector can have any number of dimensions. There is also a zero vector, which is just a point. It's also zero vector, it has a 0 length. It has no direction. Just a point. So now point P is going to have some coordinates x1 and y1, and point Q is going to have x2 and y2. Vector PQ, which is the vector that stretches from P to Q, where Q is the terminal point, is going to be calculated by x2 minus x1 and y2 minus y1. Observe my notation. I'm using these spiky brackets. Now, some notation over here. On the side, notation says if we have these guys It's either a point or open interval. And if we have these puppies, it's definitely a vector. So when you lose some points on a test because you use the wrong ones, you know why. And I put them in red over here, okay? It's not the same if you put a comma or a period as you write your essay in English. So observe notation. So now, if we go to our XY plane and pick 2 points, we can calculate the length of that vector. Now I'm going to use blue and red. The blue is going to connect this way. Maybe I should call these points A and B, that way we can see clearly. So now blue calculation is AB. Clearly A is the source, initial, very good. And B is the terminal. It's always terminal minus initial. So the x-coordinate of the terminal point is 5 minus -1, comma, 2 minus -2. So AB is 6, 4. So the vector is 6, 4 this way. Now red, I'm going to use same 2 points, but I'm going to go the other way. The red vector is BA. Now that one has A as terminal, so it's -1 minus 5, and then -2 minus 2, so vector BA is -6, -4. So we see that the coordinates of these vectors, -6, -4, and 6 and 4, these are almost the same. From where we can come up with our first formula, where vector AB is the same as negative vector BA. And we'll reinforce this as we go along. Now, major statement here is that vectors are free to move in space. You remember when I used to stand over there? Well, I'm not over there anymore. I'm here, right? I'm a vector. If I call my phone a vector, I can move this vector. You see, as long as you keep the magnitude, which is the length of the vector, and the direction, which is the angle of the vector, the same, you can place that vector wherever you want, and it will always be that vector. Vectors are free to move in space. So what I'm going to do now is I'm going to take my vector 6, 4 and move that vector so it starts at the origin. So now this is my vector with a terminal point 6, 4. Note the use of parentheses. But my vector is vector 6, 4. I'm going to call this vector u, lowercase u. Now, when you write your exams, your homework and all everything else, you will have to put this little arrow on top because that signifies it's a vector. In a textbook, what they do is they put the u bold, right? So they make it bold. And bold quantities are vectors, and the ones that are not bold are not vectors. Now, you're not going to go and try to make stuff bold as you write your exam, so you're just going to put this arrow on top, and that means it's a vector. So this vector u is vector 6, 4. It has magnitude, which is the length, and it has direction, which is the angle. Now, you are observing over there a triangle, and hopefully common sense kicks in, Pythagorean theorem to figure out the length, and a simple inverse tangent to figure out the theta for the angle. So, Pythagorean theorem, now magnitude will be denoted as the absolute value of u vector. So, absolute value in vector notation means the length. Well, actually, guys, you just maybe once in a lifetime learn that the absolute value is the length, because a lot of people just go, oh, absolute value makes things positive. No. Absolute value is the distance from the number to the origin. It's length. So if you have -3, the distance from -3 to the origin is 3. It's length. Or if you have +3, the distance from the origin to that thing is... Now, absolute value makes numbers positive. That's a consequence. That's not a definition of absolute value. Absolute value is the length from point A to origin. So now, length of the vector is going to be the length from the origin. As you can see, we placed the vector at the origin to the terminal point. In this case, we just have the Pythagorean theorem. So 6 squared plus 4 squared, which is square root of whatever. That's a 64. No, sorry, 36 and 16, right? It's 52? Yeah, whatever. This is good enough. So square root of 52. So that's the magnitude. Direction will be theta, and theta is the inverse tangent of x divided by y, y divided by x, the opposite, which is 4, divided by the adjacent, which is 6. So we are talking about the inverse tangent of 2/3. Now you can go and get your decimals or whatever if you want to, I don't care. So these are the two things that describe a vector in 2D, right? Yeah, these are the vectors in 2D only. I think next section is vectors in 3D. Yes, so 11.2 is vectors in 3D. Maybe I should add this to a title. Let me use vectors in 2D. There we go. Fixed. All right. Next section, 11.2, is going to be vectors in 3D. So now that we have these guys, we understand that vectors have the length and they have direction. And now we can start working with operations with these vectors. You can stack vectors, right? You can make them longer and shorter. So, another example of vector is this vector here. It's a marker. And you have to use this vector in a particular way to work, right? If I use this vector this way, it would not work. If I use it this way, it would not work. If I use it this way, it will work. Now, let's say that this vector is too short for my hand. I'm going to take exactly the same vector, and I'm going to put the two vectors together, and now I'm going to have, as you can see, it sits nicely over here, right? But before it didn't really sit nicely. Now it does sit nicely. So I multiply this vector by 2 by simply adding one vector to another, making it longer. So what we can do with vectors is we can add them, subtract them, and then we can multiply them by a constant to make them longer or to make them shorter. If you multiply by 1/2, you will cut the length of the vector in half. So there are these basic operations which are addition, subtraction, and scalar multiplication. Addition. Vector u plus vector v will add components of vector u to components of vector v, obtaining the new vector where the components are added together. Graphically, if you have a vector u and you have a vector v, you will move vector v because they are free to move in space. So vector v is 2, 3. So you will move vector v. You just translate that vector there. Right, that's what you do. You just move it to the right. And then this is your u plus v, the red one. Now, to move this into the writing, we have our vector u as 3, 1, and we have our vector v as 2, 3. U plus v as a vector is going to be 3 plus 2, comma 1 plus 3, which gives us the vector 5, 4. That's the red one. You know what? I'm going to write it as red one, 5, 4. Let's check if this point over here is 5, 4. It better be. If it's not a 5, 4, we pack all this stuff and that's it. No more math ever. So 1, 2, 3, 4, 5. 1, 2, 3, 4. Yep, 5, 4. So everything worked out. Subtraction actually doesn't exist. What we do is we add the first vector to the flip of the second vector, and then the addition of those two is the subtraction. So subtraction of u minus v is going to be vector u plus negative v. Graphical representation first, obviously. So say I have vector u given as 3, 2, and vector v given as 2, 4. The way we do this is we first create negative v negative, we will have -2, -4 as coordinates. Then we will go to the tail of u and work -2, -4. What I did is I took vector v and flipped it, so the arrow is now here, and moved it to the tail of vector u. Or if you know that your vector v, negative v, is -2, -4, like I did, what I did is I put this point here first, and I counted -2 from that point. So I regarded this point as the new coordinate system, as the new origin, and I simply counted -2 to the left and -4, right? What happened? I know, I can count, imagine. And now the simple sum of these two, which is u plus -v, maybe I should denote that this is -v. Hey, what happened to my arrow here? Gives me the red, and this red is u minus v. Now we better, when we do our subtraction, we better get 1 and -2, because you clearly see that this vector is 1, -2. Right, that's the terminal point. So let's work out calculations. I have u minus v, to be 3, 2 minus 2, 4, which is 3 minus 2, comma 2 minus 4, which is the red one. Yay! We got 1 and -2. So subtraction is actually addition of the first vector plus the negative of the second vector. This is not commutative, and you can go and on your own time try v minus u, in which case v stays where it is, u gets flipped, and then you again head to tail method to add them, and you will get something else. Well, scalar multiplication. Scalar multiplication is supposed to make your vectors longer or shorter by multiplying them with the numbers larger or smaller than 1. So I already showed you the example of that by using the marker and then just connecting another marker into it, making it twice as long. We can also cut the marker in half, which is a vector times a half, to make it shorter. So now, if I have vector u to be, let's say, 3, 8, then 2u will be 6, 16, and half a u will be 3 halves. That's a terrible way to write a fraction. 3 halves and 4. Now graphically you will just go halfway or twice as far. Oh, this is 16. Who picked these numbers? I'm just going to do the half. Really? So this is vector u, and then if you go halfway. This is the red one. I'll put this arrow right there. This is u over 2. 1/2 u. It's simply, it preserves, so scalar multiplication preserves the orientation. You see that addition and subtraction change the direction of the vector, right? As I added these two vectors, vectors u and vector v have different directions than the vector at the end, u plus v, and the same goes for subtraction. We started with the two black vectors, and when we subtracted those two black vectors, we got a third vector that has different direction. Scalar multiplication will just change the magnitude of the vector without changing the direction of the vector. And that's going to be important later in our calculus life. Now, quick thing that I forgot to mention earlier. Two vectors are the same if their magnitude and direction are the same. So two vectors are the same if their direction and the magnitude are the same. Okay. Now, vectors do not have to be used only for physical quantities, like I said, my height or a calculator or a marker or the length of the marker. We use vectors to show other aspects of our universe, like force. So force is something that you don't observe physically. It is something that you sense. Again, the force is going to have the direction and the magnitude. Time is only going to have the direction. Right? The magnitude, because we always move forward in time until we fix that. So when you're talking about the force, right, the difference between are going to be just the pure magnitude of the force, and then obviously the direction is, direction, which way the force is applied. Now you're going to have a circular force as well later on, which we are not dealing in this class with, and that is going to be the torque. Actually, we will deal with that, but different, which is the force that deals in circles, because you also have a circular kinematics. You know, where you measure instead of using linear meters or feet, right, you will use the angle, and then you will have angular velocity with omega and angular acceleration, alpha. So also the force can act that way, and we have, again, polar coordinates deal with that thing, because we can have vectors do those things as well. Now there's more stuff that we are supposed to discuss, mainly the properties of vectors, and that would close. But since these properties are the same for two-dimensional and three-dimensional vectors, we are going to actually deal with these properties next class together with 3D vectors. So that's it for today. Let me just say bye.